Alright, we're going to talk more about stereochemistry and chirality, and in particular we're going to focus this video on enantiomers. And this is kind of the key concept in stereochemistry, if you will. And the idea is basically that you can have molecules that are almost exactly the same, but the only real difference is that they curl differently. And we call pairs of molecules that are like that enantiomers. They are non-superimposable mirror images. Your left hand and your right hand are the quintessential example of enantiomers. Your left hand and your right hand curl differently in three-dimensional space, but you cannot put them on top of each other because they are mirror images that cannot be superimposed. Again, they curl differently. For the same reasons, your right foot and your left foot would also be enantiomers of each other. So anywhere you have a relationship where the molecule is identical except that they curl differently in space, then what you're talking about is a pair of enantiomers. And again, by definition, that means that they cannot be superimposed because they are going to point in the wrong direction, but they are mirror images of each other. Moving away from the realm of your hands to the realm of molecules, one thing that is often true about pairs of molecules that are enantiomers is that they will have one or more stereogenic centers. This is not always the case. You can definitely have enantiomers that do not have stereogenic centers, but often, most often, a pair of enantiomers will be a situation where you have a molecule that has a stereogenic center and its partner, the other enantiomer, will have that stereogenic center flipped. So often they will have a stereogenic center. In other words, a stereocenter is usually the way it's called. And what you're looking for in a molecule would be a place like this carbon right there, which will have four unique things bound to it. So this carbon is a stereogenic center, and that's because it has four unique items bound to it. Most frequently in the land of organic chemistry, if you have a stereogenic center, it is a carbon atom, but it doesn't have to be. Any atom that can tolerate having four different things bound to it can be a stereogenic center. So again, it's often carbon, and it always must have four things bound to it. If you have a carbon atom that has, say, two hydrogens bound to it, it cannot be a stereogenic center. We'll talk more about that later. So what we have here is an example of a molecule that has one stereogenic center. Therefore, it can have an enantiomer. Therefore, if you would like to generate the enantiomer for this molecule, what you have to do is generate the mirror image of it. And if you see a dotted line drawn somewhere, what that's suggesting is that this is going to end up being the mirror plane in which we reflect everything. And the easiest way to reflect something is just simply draw it again on the other side in such a way that everything is mirrored. So the H's are both up because that's the same way, but the F's go in the opposite direction, and then the bromine will come toward and the chlorine will go back away, and now I've generated the mirror image. So what I've done is generate a non-superimposable mirror image. Now, I clearly generated a mirror image, and you're going to have to take my word for it at the moment that these are non-superimposable. But again, this is the stereogenic center in both cases, and what's going to be true eventually, once you learn how to assign these, is that you can recognize that the stereogenic center has flipped. This, as drawn, you will eventually learn, is the R form of the enantiomer. When you assign it, you will call it R, and this right here would be the S form. Another key point to make here is that if you are trying to generate an enantiomer, one way you can do it is exactly the way I did. You draw the mirror image, so you draw a mirror plane and then reflect it, and that will create enantiomers. But the other way to do it is to flip all stereogenic centers in the molecule. In this particular case, what we have is a single stereogenic center, so if you flip that one, then you have an enantiomer. But there will be cases where you will have multiple stereogenic centers, and in those cases, in order to generate an enantiomer, what you must do is flip each and every single one of the stereogenic centers that are present. In other words, again, the molecules have to be non-superimposable mirror images. In a sense, your right hand and your left hand are single stereocenter type molecules. One hand curls one way, the other hand curls the other way. The last key point to make about enantiomers is that they are not that different. Again, your left hand and your right hand are almost identical. The molecules themselves are identical in every single property except one. They rotate plane polarized light in different directions. Now, it is the case that you can label these as R and S, and R stands generally for right-handed and S is sinister, stands for left-handed. These assignments, however, do not tell you which direction the plane polarized light is rotated. And in fact, the plane polarized light can be rotated to the right and to the left. But The only property that's different between a pair of enantiomers, between the molecules in the pair of enantiomers, is which direction they rotate plane polarized light. However, because the shape is different, because the curl is different, then the molecules will interact with other molecules that are chiral in different ways, so you can differentiate them from each other. It is, however, the case that if you are running a reaction that is achiral to begin with, and it generates a stereogenic center along the pathway of the reaction, then that will most often create a racemic mixture. In other words, a 50-50 mix of the two enantiomers. If you have a single one, you have a single enantiomer. If you have both molecules together in equal proportion, a 50-50 mix, then that is called a racemic mixture. So you have a racemic mixture of your hands. You've got the left-handed one and the right-handed one. You have a racemic mixture of your feet as well. These molecules, if they are present in the 50-50 mix, if you have a racemic mix, then the overall mixture will not rotate plane polarized light. I've already mentioned that there are many valuable molecules out there where you want a single one, a single enantiomer, like drugs, like amino acids, like food, like fragrances, all sorts of things where you want to isolate one or the other. And for that, what you really need to do is find a way to differentiate them. And again, they're only different on two parameters. One is the way in which they rotate plane polarized light, and the other is the way they interact with chiral molecules. So a lot of organic chemistry is about trying to generate only the enantiomer you want at the time you want it. And to the extent that you need to purify things, then there are methods that you can use to purify a racemic mix to end up with a single enantiomer. But all things being equal, it's better to just generate the one you want in the first place rather than generating a 50-50 mix and needing to throw away half your stuff.
So here all I wanted to do was take a moment and show you how the two enantiomers look in Chem 3D, which is a drawing program. And this right here is a hydrogen atom, this is a bromine, chlorine is green, and fluorine is yellow. And so you can tell that these two molecules are almost the same, but not quite the same. And the green is toward us, here the yellow is toward us. So since the red and the white are oriented the same, if you try to put them on top of each other, I hope you see that the yellow and the green would end up in the wrong place. They cannot be superimposed. And so I'm going to help illustrate that a little bit by just rotating through them slowly here. And again, so this is now a top-down view. We're looking down on the hydrogen, rotating around just a little bit more. You get the idea. These molecules are nearly identical. They're mirror images, but they cannot be superimposed. Here's the image where you're trying to superimpose them this way. Again, no matter what, the green and the yellow are always going to end up on the opposite sides when the white and the red are oriented the same way. This is the way enantiomers always are. They will be mirror images. We could rotate them so they were obviously mirror images to each other, but they cannot be superimposed. Okay, now I've rotated them so they're rather more obviously in mirror image orientation, which is to say the hydrogens are straight up and down and the fluorines on our opposite side. So this is the image that I had on the board. Sorry, actually, I'm lying. The red is the bromine. So anyhow, the bromines are opposite each other. So this is not the image on the board, but it is equivalent to the image of the board. And again, you can tell that they are mirror images of each other. So they're mirror images that cannot be superimposed. They are enantiomers.
To reiterate enantiomers, what we have are non-superimposable mirror images, and your hands are the classic quintessential example of enantiomers. If you would like to generate an enantiomer given a molecule, what you do is you draw the mirror image of it. And the way you can do that in some sense is by flipping stereogenic centers if present, but they don't have to be present. You can have a pair of enantiomers that doesn't have a stereogenic center. A molecule can be chiral without any one spot in the molecule being the chiral spot. We'll get into some examples of that later. That's called axial chirality. But if you have stereogenic centers, then flipping all of them leads to the other enantiomer. If you have a mixture of two enantiomers, 50-50 mix, then that is called a racemic mix. And generally speaking, you are trying to avoid generating those in synthesis because a huge amount of effort in organic chemistry is devoted to separating enantiomers from each other. So the last key point is that the only chemical difference between enantiomers is that they rotate plane polarized light in opposite directions, but the fact that their shape is slightly different, which causes that rotation of plane polarized light in opposite directions, then different chiral molecules will interact with them differently. And that's the way in which you can exploit subtle differences in shape to separate them from each other. One way of purifying a racemic mixture is to run your sample down a chiral column, so the column itself has chirality, and then one enantiomer or the other will move faster through the column than the other. And that's how things can be separated.